math scar. It has all this formula on it. So when I take exam, I can look at it. Today, we're going to go over 7.4, integration of a rational function by partial fractions. Here's one example of a rational function. So it is basically it's a polynomial divided by polynomial. So that is called a rational function. Like rational number will be integer divided by integer, right? So rational function will be polynomial divided by polynomial, providing the denominator is not so. All right, so today we're going to learn how to integrate a rational function like this, polynomial divided by polynomial. We're going to do that by something called partial fraction. So first consider this. When we have this one subtracting by this, okay, these two actually are called partial fraction. So when I combine these two, I will take the common denominator, right? Then this common denominator will be x minus 1 times x plus 2. I want to combine them this way, and we simplify the numerator on top. I got this, and then finally I got to this one, okay, which is a polynomial divided by polynomial, which is a rational function right here. But when I do it this way, I know this is equivalent to this. So which means that could be expressed in terms of this subtracting this, okay? So when I integrate this rational function here, which is this one, the same one that you have over here, I can decompose it into this part, the sum or difference of these partial fractions, okay? So because that is equal to this, okay? So what's the advantage of expressing this into this? Why do we want to decompose that into this sum of difference of partial fractions? Okay. Now, if you look at the next step over here, you see that if I decompose this into this difference of these two partial fractions here, I can actually separate them this way, right? So will be the 2 here is a constant multiple, so outside. And then integrate 1 over x minus 1 over here. And then subtract the integral of this 1 over x plus 2 over here. Okay. Am I going too fast? Okay. All right. So now we get to this step. Okay. Now when we get to this step, okay. Now remember, I put a note over here. Okay. So before we talk about the antiderivative 1 over u with respect to u, it is ln of the absolute value of u plus a constant, right? So this one here will be similar, okay? So what's the antiderivative of 1 over x minus 1 with respect to x? What function when you differentiate give you 1 over x minus 1? Think about this, okay? Think about this as the u, okay? So you can do it yourself, okay? So du will be equal to dx, right? Okay. So basically this one here is the integral 1 over u du, right? So we can use this formula here, okay? So we'll have 2, and what's the antiderivative of 1 over x minus 1 with respect to x? According to this formula here, what would that be?
Ln of the absolute value of x minus 1.
Good job, okay? All right, so that is ln of the absolute value of x minus 1.
So you don't even need the u, really.
Yeah, you don't need the u, really. Yeah, that's the point. Okay, so you can just think about this as that, okay? So you don't need the u over here. You don't need that, okay? So go ahead and put that. Okay, now minus, then this one here is similar. You don't need to put a u there. You can think about this as a whole quantity like this one over here, right? So what's the antiderivative of this over here? Similarly, will be ln of what? The absolute value of
x plus 2.
Plus 2. You got it, okay? And then finally, plus a constant. Okay, you guys did a good job, okay? So over here, you could leave like this. However, you can also combine them, okay? you can combine this, just leave them like this, okay? So I have this extra, okay? So we don't need this. Don't need this one right here. So that's the answer there, okay? So you see how this partial fraction here is going to help you. So when you decompose this rational function into the difference of these two partial fractions, you're able to find the antiderivative this way, right? Okay. So you might ask, is it every rational function can be decomposed into sum or difference of partial fraction? The answer here is yes. Okay, so it is already proven. Okay, so it is proven that any rational function can be decomposed as the sum or difference of partial fraction. So what do you mean partial fraction? Okay, like this one here is a partial fraction. Okay, and this one is a partial fraction. Okay, notice that partial fraction here, the denominator will be a polynomial either of degree 1 or degree 2. Okay, no more than that. Okay, so degree 1 or 2 in the denominator. Okay, those are called partial fraction right here. Okay, now I'm going to outline the steps in integration of rational function. Okay, so what are the steps? Okay, so I'm going to outline that for you guys. Okay. So when you have a rational function, which means you have a polynomial divided by polynomial, the first step over here is you want to see if the degree of the numerator is greater than or equal to the degree of the denominator, then the first step here is you're going to do long division first. Okay, so and then write that as a quotient plus a remainder over divisor. So do you guys remember how to do long division? I think in Math 60 and Math 90, we went over long division. Okay, but if you guys don't remember, I'm going to briefly review this for you. Okay, so this is a rational function. This is degree 2, this is degree 1. Okay, this degree is greater than this degree here. So we're going to put this down here and the divisor outside here. And this is the division side. Okay. So you look at the one that has the highest, this one over here, it has the highest power on x. Okay, think about x squared divided by x. What's x squared divided by x? That's equal to
X.
Right, you got it? Okay, so that's equal to x. Okay, so you will put it over here. Put it here, okay, x. Okay. Now you're going to distribute this. Okay. So just like how you do division for a number, right? So multiply x with x, you get x squared. And then x times -1 is negative x. When you do division, and after that you will subtract, right? So we'll subtract right here. Okay. Subtracting over here, this two cancel. X minus x give you 2x. Okay. Now over here, now you have to think about this 2x divided by x. Okay. So 2x divided by x over here, it is equal to 2. I'm going to put this 2 over here. So plus 2. Okay, so put it over here. Okay. So now you're going to use this 2 to times x here and times the -1 here. So then you get 2x minus 2. After that, you subtract. That's how you do division, right? Okay, subtracting over here, this 2 cancel. Okay, so you have 0 minus 2. So what's the remainder over here?
-2.
Almost. Try it again. Okay, minus.
Oh, no, I mean 2. Positive 2. Plus 2.
Yeah, you get positive 2.
Right,
okay.
because subtraction.
Yes. So this is a remainder. Okay. So that's how you do long division for polynomial. Okay. So after you have do this, done this long division, then this divided by that, the quotient part will be this. This is the quotient. So we're going to put it over here. X plus 2, which is a polynomial over here. Okay. Now, this part over here, you have this remainder over divisor. Okay, remember, remainder over divisor. Remainder over here, it is 2. The divisor here is x minus 1. Okay, so this rational function here is equal to this polynomial plus this remainder over divisor over here. Are you guys good? Okay. Now notice that when I say that the degree over here is greater than or equal to degree down here, then you have to use long division first to write it this way. If they both have the same degree, say degree 2 and degree 2, you still need to use long division. Okay? So say this is x squared and this is x squared, then you still use long division first. Okay, now after this.
Wait, so that technique only works with when the top exponent is greater?
Greater than or equal to the exponent down here.
Okay, but if the bottom one is greater, then it doesn't work.
Yeah, then you don't need to. Then you don't need to go to
then okay,
long division. Then you can go to the next step. Okay.
Yeah, gotcha.
So this is the first step. Okay. Okay. Now we have used long division, and we write this as this polynomial, this quotient. This is this polynomial, and then the remainder here it is 2. The divisor is x minus 1. Okay. So we have this. So we write this into this polynomial plus this remainder over divisor. Okay, so that is going to make it easier for us. Okay, now for the polynomial part, okay, this polynomial part over here, we can just integrate that term by term. Okay, so tell me, what's the antiderivative of x over here? So you get x squared over 2, right? And then maybe I should use a different color then. Okay, so we'll get x squared over 2, okay? And then plus antiderivative 2 here, it is what? It is 2x. Yeah, you got it. Okay, now what about this part right here?
That's just going to be 2 natural log x minus 1, absolute value of x minus 1.
Good job. Okay, nice. You guys get a hand of it. That's good. Okay, so absolute value of x minus 1. And don't forget to press a constant. Okay, so press a constant at the end. Okay, so it works. Okay, so in this case, this part here, this is already a partial fraction. So yeah, so the first step is when the degree up here is greater than or equal to the degree down here, then you use long division to rewrite this way. For the polynomial part, you will just integrate that term by term, and this part here you can deal with them this way. Okay. All right. Now, ready to move on to the next step? Okay. Are you guys good?
Yeah.
Okay. So the next step over here, now we're going to focus on this remainder over divisor part. Okay. So now this part over here. This part here, in this case, you don't need to do anything, right? You can just go ahead and get the antiderivative, right? But sometimes it's different, okay? It's like something like this, okay? So when you have this remainder over divisor part, it's like this. So we're going to move on to the next step, okay? So you're going to factor the divisor over here as far as possible. Factor this as far as possible, okay? So the denominator here is x squared minus a squared. How can we factor this? What would this be?
I think x plus a times x minus a.
Yeah, you got it. X plus a times x minus a, right? Okay. Now, what about this one? If the denominator is like this, can you factor this as far as possible? Factor this completely. X minus 2 times x plus 2, right? What about this x squared plus 4? What do you think? That one over there, it is actually...
I don't think it's factorable.
Yeah, it cannot, right? Okay, it's not. So it is something we call irreducible quadratic. Okay, quadratic, has something to do with the square. So if it's degree 2 over here, this polynomial here is called quadratic. Okay, it's irreducible. That means you cannot reduce it any further. So how can you tell it's irreducible? Is there a way that you can tell it's irreducible? Well, remember the quadratic formula, right? This part right here inside the square root. When this part inside the square root here, it is negative. Square root of negative is not a real number, and you will get no real solution, right? Okay. So when this part over here, that we call delta, okay, it's called the discriminant. Determinant or discriminant? Okay, never mind. Okay, so when b squared minus 4ac over here, it is a negative number, then this quadratic is this quadratic polynomial over here is going to be irreducible. Okay, so you can tell by looking at this b squared minus 4ac. Now, in general, if you have an x squared plus a positive number, that's irreducible, like x squared plus 4, x squared plus 9, etc. Okay. Now, this one here is also irreducible. How can I tell? I look at the b squared minus 4ac. Okay, that turned out to be negative. Okay, so that's irreducible also. That means you cannot factor that down any further. So it has to remain degree 2. Okay, you cannot break it down into degree 1. Okay. Question? Okay, so it is proven that, okay, so this is any polynomial can be factored into factors that are either degree 1 or degree 2. Okay, no more than that. Okay, so you can all break it down into factor, either linear or irreducible quadratic. Okay, degree 1 or degree 2. Okay, so what happens if you have a degree 3? Then that means you can still break it down. Okay, you can still break it down into degree 1 or 2. Okay, so this is proven. Okay, now let's try to. Okay, so that was the second step. Okay, second step is to factor this denominator over here as far as possible. Break it down into degree 1 or degree 2 factor. Okay. Okay. Now, step 3. Step 3 is the part that you decompose it. Okay. So decompose it. So you will rewrite this rational function as a sum or difference or partial fraction. So let's practice on this. Okay. So we have actually 4 cases. Okay. So the first case here is the denominator is a product of distinct linear factors. Okay. For example, like this one and this one. Okay. So they're all different. The linear factor over here are different. Okay. They're all different. Okay. How can I decompose this? Okay. Now to decompose this, then the first one here will have the x minus a in the denominator. The second one over here will have x plus a in the denominator. So basically, you just take each factor over here and put them into a separate partial fraction right there. Okay. Now, what should I put on top? Okay. The one that you put on top, okay, see over here, this, see, those are linear, right? So those are linear. So those are degree 1 to the first power, right? Okay. So they're degree 1. So up there in the numerator, so you're going to put a and b. Those stand for numbers, okay? Those are the numbers that we need to find out later, the A and B. So for now, we just put A and B. And then later on, the next step, we find out what A and B here. Okay, so that's how you decompose it. All right, okay, how about you do the second one? Okay, so what does this decompose into? The first one.
A over X.
Yes, you get A over X. Okay, let's just put the denominator here first, X. And then X minus 3, and then 2X minus 1. And then, yes, up here you put A. And then here will be B. And here will be C. Okay. And ABC will be number that you need to find out later. Okay. The first case good?
Yeah.
Okay. All right. Okay. The second case over here. Okay. So when the denominator here, they're all linear. Okay. Like this one, all linear. But some are repeated. And someone said, wait a minute, this is not linear, right? It is considered as linear, X and X over here considered linear, but repeated twice, okay? So X squared here, we consider that as this two linear factor, X and X, repeated twice, okay? So some are repeated, so repeated twice over here, okay? This one over here, it is a linear factor, X minus 1, but repeated 3 times. Do you guys get it? Okay. So a common mistake here, sometimes the student forget, this is actually linear factor repeated twice, okay? So it's not quadratic, it is linear factor repeated twice, okay? Okay, so to decompose this, we'll put down the denominator for the partial fraction. So the first one here will have X, okay? And then the second one will have X squared, okay? So every time you're going to go up by 1. So the exponent over here, from this to this, the exponent is going to be up 1 until you reach the maximum power, until you reach this maximum power over here, which is 2. So similarly, okay, what do you think I should put over here? This, and this.
X minus 1 for the first one.
Yes, X minus 1. And then next one?
X minus 1 squared.
X minus 1 to the
third power.
Yes, and then you stop, right? Because this is the maximum power over here, right? Okay. Okay. All right. So, so we know the denominator here. Okay. So what do you think I should put on top over here? Well, those are all linear. Remember, those are all linear factor, right? So up here, you have all number, okay? So you have A, B, C, D, E. As long as you know your alphabet, okay. So, so A, B, C, D, E. The reason for that you put only number, A, B, C, D represent number, is because the factor down here are linear. So it will be 1 degree lower, so those will be number, okay? You guys good? This is second case. Okay.
Yeah.
Okay. Now the third case over here, when QX, the denominator over here, contain irreducible quadratic factor and not repeated, okay? So like over here, you have linear and these two are irreducible quadratic and then they're distinct. They're not the same. They're not repeated. There's no square over here and square over here, okay, or Q, okay? So how can we decompose that into the sum of partial fraction, okay? Again, you're going to take this factor. So this linear factor, we have x minus 1. That'll be for the first partial fraction. And then the second one, x squared plus 1, okay? Because they don't repeat, right? So we just use each one over here. Okay, so x squared plus 4 over here. Okay, now notice that this is going to be, this is degree 1, right? This is degree 2. This is degree 2, okay? So now because this is degree 1, then this will be 1 degree lower than this. So I will just put number. So just put number up here. So that I'll just put A. What about this? Degree 2. What should I put on top?
B.
Almost. Okay. B, remember it has 1 degree lower, right? So it has to be degree 1. Degree 1. 1 degree lower. Because this is degree 2, degree 2. 1 degree lower will be degree 1. Okay. So degree 1, so that means linear. So you will have this bx plus c. So it has to be linear. So up here, that will be 1 degree lower than that. So we have a linear factor. We have a linear expression here. Okay, bx plus c. Similarly, this will be also linear. So it will be, so they're going to be dx plus e. Any question here?
So the top always has to be 1
Yes.
degree less.
Yeah. It has to be less than the degree of the denominator in order for that to be proper. Yeah.
That's why A is up there because it's degree 0.
Yes.
And that's degree 1. Okay.
Right. Just like proper fraction, the number on top is smaller than the number in the denominator. So for polynomial, those are called proper polynomial when the degree up here is less than the degree down here. Okay.
And then
Uh-huh.
when we go to like solve these in the homework, will the A's and the B's and the C's, will those be replaced by real numbers, or will we actually answer them in the form A plus B?
Yeah, good question. Those is the we're going to solve for A, B, C, D, E later on. Okay.
Okay.
Yeah. We're going to find our A, B, C, D, E are. Okay. Okay. Now we get to the fourth case right here. Okay. When the denominator over here contain repeated irreducible quadratic factor, like this one over here. See, both of them are irreducible quadratic over here, but this one here repeated 3 times. Okay, so repeated 3 times. So how should we decompose this into partial sum or difference of partial fraction? Okay, so the slide before is really long. It has 6 of them. Okay, so the first one over here will have this. The first linear factor x, it doesn't repeat, so only 1 time. Okay, and then this one x minus 1. This one, it doesn't repeat, x squared plus x plus 1. And then when we get to this one, guess what should I put over here then?
X squared plus 1.
X squared plus 1. And then the next one.
X squared plus 1 squared.
X plus 1 square, right? Okay, square. Okay. And then the next one over here, x squared plus 1 to the third power. So once you reach this maximum power, then it's okay. All right. So let's think about what should I put on top. Okay.
A.
A. Yeah, we got A, and down, and this one will be B because it's linear. What about this one? What should I put here?
That would be CX plus D.
Yes, CX plus D. Yes, the right alphabet. Okay, CX plus D. Okay. Okay, what about this next one?
EX plus F.
Right, good job. Okay.
I'm going to go through the whole alphabet.
Yes. Okay, we're gonna go through the whole alphabet. You can sing this, right? Sing it that in music. Okay. Right, and this will be. I'm not gonna test you guys something like this. It'll be too hard for you guys. Okay.
Is it GX to the third?
GX plus what? Yeah. Did I skip anything? That's H. And the next one here will be
IX plus J.
J. Yes, you got it. Okay.
I was thinking it was going to be GX to the third because when you multiply that bottom fraction out, it turns out to be X to the fourth.
And remember, this is considered quadratic, but repeated 3 times. So if it's quadratic, then this is going to be linear up here. So just like before, this is considered quadratic repeated 3 times. So up here, it's still linear. Okay? Yeah, that's a good question. That's a very good question. So this is considered quadratic repeated 3 times. So we will have linear up here. Okay? So let me make a note over here. So remember, this is irreducible quadratic. Okay, and this is irreducible quadratic, and it is that repeated, and they're just repeated. So therefore, up here you will have linear. So you add this. So then you will have degree 1. Okay.
Okay. Yeah.
Degree 2. Okay. Okay. All right. So you guys did a good job. Okay. Ready to move on? Okay. So let's try this one. Try this out. Okay. So this one over here, we're going to decompose it. The first thing we do here, well, remember the degree up here is less than degree down here. So you don't need to use long division. So move on to the next step. So we're going to factor this denominator as far as possible. So you guys already did this. So which is going to be x minus a times x plus a. And then you decompose it, right? Remember how we decompose it? First one, it is what? A over x minus a. And then second one was b over x plus a, right? So we decompose it this way. Now we're going to find the a and b, okay? So to find this a and b, first thing we do here is we're going to multiply this side and this side here by the LCD. What's the LCD of this? The LCD will be, well, the LCD will be just this one here, right? Remember? Okay, this is the LCD.
Let's multiply.
Yeah, multiply. So that's the LCD. So we have x minus a times x plus a. We're going to multiply this LCD on this side and this side. Okay, so multiply this with this one, we got 1. So we got 1 over here. And then equal to, using this to times this one over here, we got a times x plus a, and then adding b times x minus a. You got this? Okay. Now, there are 2 different methods to find the a and b here. Okay, I'm going to go through them, and you can choose whichever method that you prefer. Okay. So how can I find this a and b? Okay. The first method here is to multiply out and combine items. So multiply this out and combine items. Okay. So we'll have, so we have 1 over here. On the other side, we'll get this. Okay, remember when you multiply this out, you got this ax plus AA, okay, and then plus bx minus BA, okay, and you combine items, okay. So you combine the extreme together. So there's the extreme, okay, so you have 1 here. So the extreme over here, and then not extreme over here. So the extreme here will have this a plus b as a coefficient. And then the rest over here, we have this a minus b. Okay. Okay, so far so good? You got this part? Okay. Now, after that, you're going to equate the coefficient, okay? So 1 equal to this, and this is true for all x, okay? Remember, this is true for all x, okay? So what do you mean here? Okay, this is true for all x, note. So this is true for all x, okay? So what happened over here, it is, so let me give you one example, okay? So say, if you have, say, 2x plus 5 equal to ax plus b, and if this is true for all x, then what can we say about this a? A here will has to be equal to 2, right? And then b here has to be equal to 5, if that's true for all x, okay? So over here, because this is true for all x, so now we're going to equate the coefficient, okay? So this one over here we have, this is the same as 0 times x plus 1. So we know there's a plus b over here. So a plus b over here will be equal to 0, okay? And this part over here will be equal to 1. So we equate the coefficient. So we have this a plus b will be equal to 0. And then we have this a minus b times this a will be equal to 1. Okay, equal to 1. Now we just need to solve for a and b. Okay. Do you know how this? What do you suggest? How about we take this, the second one right here. Let's divide both sides by small a. Then we get a minus b is equal to 1 over small a. Okay. The reason I want to do this is because now you have a plus b, now you have a minus b. If you add this 2, what do you get? If you add this one and this one,
it's just 1 over a, right?
Yeah, if you add them, then you get 2a equal to 1 over a, right? Then you get 1 over a. So which means that a is equal to what? A is equal to 1 over 2a, right? Okay. So from this, we're going to get this. Okay. You got it? You get a. Now you can get b. If you know a, you can get b, right? So what does b equal to? Well, from here you see that a plus b is equal to 0. So a and b are opposite, right? So b here will be equal to opposite of this. So opposite of 1 over 2a. So you find this a and b here by solving this, by equating the coefficient over here, and you're solving this system of 2 equation to get a and b. Okay? Question? Yeah, the algebra always is, you need the algebra, how to solve system of 2 equation. Are you good? Okay, so that was the first method. You probably don't like it. Now I'm going to give you another method, okay? So the second method over here to find a and b, we plug in special values of x. So what do you mean special values of x? Okay. So let's think about the LCD. Okay, so the LCD over here. In this case, the LCD was x minus a times x plus a. Okay. Okay. So what are the jaws of this? The jaws of this LCD are what?
A and negative A.
A and negative a. Yes, you got it. Okay. So we're going to plug in a and negative a. Okay. So I'm going to plug in a and negative a. Okay. So let's plug in a and negative a over here. Okay. So if I plug in x equal to a, okay, let's take a look here. Okay, I'm going to plug this into this equation. Okay. Are you able to see it? Okay. Into this. Okay. So if I plug in x equal to a, then what happened over here is on the left side is always 1. On the right side, if I plug in x equal to a, then this part will be 0, right? X minus a is going to be 0 when x equal to a. So this part will be 0, and only this part here is a y. So 1 is equal to this capital A over here, and then times 2a. Okay, times 2a. And that is going to give us, this a over here. Capital A is equal to 1 over 2a, right? It's the same result as what we got from the other side, from the first method, right? Capital A is 1 over 2a, right? Okay. Okay. Now go ahead and plug in x equal to negative a right here. Okay. If I plug in x equal to negative a, then this part here will be equal to 0, and only this part here is a y, right? So what do I get? 1 equal to, okay, the second part over here will be b times negative 2a, okay? So solve for b. So b will be equal to 1 over negative 2a. So let's put the negative side in front. Let's put the negative side in front. So negative 2a. Okay. It's the same result, right? Okay. Okay, so
I'm sorry,
you,
where did you plug it in?
we plug it into this equation.
Oh, okay, I see.
Did I somehow? Okay.
No, it's okay. I got it.
Okay. So into this. Okay. All right. You guys good? Okay. Now I'm gonna, once you file A and B, now we can decompose it, right? So
I think I like that method better.
What?
The second method better?
Yeah.
Yeah. I think
it's better.
It's a lot less work.
I know.
Gosh.
Okay. Yes. Okay. So now we can decompose. Remember, the first partial fraction has x minus a in the denominator. The second one has x plus a. And then at that time, we say we figure out this a and b. Now we figured this a and b out already. So the first one here is what? 1 over 2a, right? And then this one is negative 1 over 2a. Now this one here is a a, right? This one here is a b, right? So we just found out a and b. Okay. Now we're almost done. Okay. So over here, 1 over 2a is a constant multiple. So let's bring it out in front of the integral. So we have 1 over x minus a plus 1 over x plus a. Yes. Okay. Now I'm going to ask you guys what would be the untitledity of this. Okay. So what's an untitledity 1 over x minus a?
The ln.
Yes. Right. So that is ln of absolute value of x minus a, right? Okay. And then this one will be ln of.
Wouldn't it be minus 1 over x minus a minus 1 over x plus a?
Joey, one extra credit for you. You caught my mistake. This is minus. Okay. This is minus. You pay attention. That's great. Okay. This is minus. Okay.
It was a test, I see.
Yeah, it's a test. You pay attention or not. Okay. So it is minus. Okay. Express a. Okay. Now, this is actually done. However, we can actually simplify this. Remember, when you have the difference of 2ln, you can actually combine this. You can also write it this way. So this is ln of a quotient, okay? The absolute value of x minus a divided by x plus a. So you can leave it like this, or you can combine these two into this way. They're equivalent, both are right, okay? You guys good? Okay.
Mm-hmm.
Do you think you guys can do one more? You think you guys can do one more? Okay. Let's just do one more, okay? The last one. Okay, like this one here. Do I need to use long division?
No.
No, you don't need to. Because the degree up here is less than the degree down here. So no need long division, okay? So over here, so the degree of P is actually less than degree of Q. Then no need long division. Okay, so and then we go ahead and factor. We're going to factor this denominator right here. Remember, so the next step was to factor. Okay, so what does the factor into? So see the factoring actually come into place right now. So first thing we take out the greatest common factor. In this case, will be just x. Right? Yes, you got it. So that's just x. And then we have 2x squared plus 3x minus 2. And then we can still continue to factor this, right? So you have this x. Now to factor this quadratic right here, then I can use try and error, okay? So the way I do it is this one. So I'll try to think about what will be a factor of 2. I can try 1 times 2. What will be the factor of negative 2? I can try 2 times negative 1, okay? And then over here, I can cross multiply and add. So when I cross this 1 times negative 1, it is negative 1. 2 times 2 here, it is 4. And they sum up to this 3 right here. Then I know this is right. So I will factor. So I will have this. This stands for x. Okay, remember the x squared over here? Factor into x times x. So when you read that, you will read this horizontally. So x plus 2 times 2x minus 1. Okay, so you have x plus 2 times 2x minus 1 over here. Okay. Okay, so that is going to factor into this. Okay, and they're all linear, right? Okay. Now we're going to decompose this. Okay. This is really long. You guys think you guys can spend about 10 minutes on this, right? Okay. So we're going to decompose this. So x squared plus 2x minus 1 over 2x cubed plus 3x squared minus 2x. So we're going to decompose it now, okay? So it's going to decompose into the sum of partial fraction. Since we have two distinct linear factors, so we have two partial fractions. So the first one we have x in the denominator, x plus 2, 2x minus 1 here. So what should I put on top? What should I put up here?
A.
A, okay. All right. So A, and then here will be B and C because they are linear. So up here will be number. Okay. Drink some coffee. Okay. So over here, because they are all linear, right? So therefore up there will be all number. Okay. Now let's multiply this both sides with the LCD. Actually, the denominator over here, let me just put the factory, right? Now multiply both sides by the LCD, which is going to be x times x plus 2 times 2x plus 1. Okay? And let's see what we get. So this side over
Minus
here.
1?
Yes. Minus 1.
Yeah.
Yes. Okay. You got it. Okay. Okay, so this will be x squared plus 2x minus 1. And then this one here will be a times x plus 2 times 2x minus 1. Okay, and then plus over here will be b times x times 2x minus 1. And then plus this one will be c times x plus 2. Okay. All right. Now, to find the ABC, which method would you like to find? Do you want to use the first method or the second method? You have a choice. It's a free country.
Second.
Second one, right? Okay. So let's find ABC. Use the second method. Okay. To find ABC, let's use the second method. Okay. Okay. So the second method say we're going to plug in. Okay. Plug in the zeros of the LCD. Zeros of the LCD. Okay, the LCD over here is what? This is the LCD. Okay, this one right here, which is this x times x plus 2, 2x minus 1. Okay, so what are the zeros?
0,
Yes,
-2, and 1/2.
yeah, so that will be 0, and then -2, and also 1/2. Right? Okay, you got it. Okay. So you're gonna plug this into we're gonna plug this into this. We're gonna plug that into substitute this. Okay, so let's plug in x equal to 0. Okay, so x equal to say 0. Okay, you guys want to try? Okay, so you plug in x equal to 0, then this part over here, the left side here will equal -1, right? So you get -1, and then plug in 0 on this side. What do you get? Well, this two term will be 0, right? When you have x here and x equals 0, so this 2 will disappear, will become 0. Only this one survives. So you get 2 times -1 times a, which is what?
-2a.
-2a. Yes, you got it. Okay, so then you get -2a. Okay. Now from here, you're gonna get this capital A over here is equal to 1/2. Right? Okay. Now I'm gonna ask you to substitute x equal to -2. When x equal to -2 over here. Okay. Now I'm gonna just tell you. Okay. Okay, x equal to -2 over here. So you're gonna substitute this -2 then square, then square, plus 2 times,
I think it's -1 again.
-2, okay, and then minus 1, okay, and then on the other side, when you have -2, then this is going to become 0, this is going to become 0 because it contains the factor x plus 2. So this 2 becomes 0, only this one survives. So you have this b times -2 times -5. And then from this, you're going to get b is equal to -110. It's -110. Okay. Similarly, x equal to 1/2. And you just substitute. Okay, so you substitute 1/2. When x equal 1/2, then this factor will become 0. So only this one survives. So you have c times 1/2 times 5/2. So over here, it is going to be, c is going to be equal to 1/5. Okay. So you figure out the ABC. That might take you a while too. If you could sit down later on, you can sit down and try to check the calculation. Over here, it is going to decompose x times x plus 2 times 2x minus 1 dx. So it's going to be decomposed into, so the first one here will have this x in the denominator. And then the a here, it is 1/2. The second one over here, it is -110. And then you have this x plus 2 dx. And then the last one here, you have this 1/5. Finally, it is 2x minus 1 dx. Now, everything will be much easier now. Okay, you guys okay with this?
Yeah.
Okay, good. Okay, so then this is going to be equal to 1/2. What's untitled 1 over x with respect to x? What do you think this? What do you think this one is going to become?
It's
Uh-huh.
Did I get that wrong? Yeah, this is natural log.
Yeah, natural log. Yes, you got it. So ln of the absolute value of x, right? Okay. And then similarly, this one over here will have this -110 is a constant multiple. Okay, and then again, natural log of this absolute value of x plus 2. And then what about this part right here? What do you think? The 1/5 is a constant multiple. What about the antideuty of 1 over 2x minus 1? Again, it is going to be Ln of absolute value of 2x minus 1. However, we need to fix it because if I differentiate that, I'll have to multiply by 2 in front, right? So to cancel out with the multiplication with 2, what do I need to do over here? You will divide this by 2. Okay, so you can try this at home. Try to differentiate Ln of the absolute value of this, and then later on divide by 2 over here. Okay, you will get back to this. So basically, it's Ln of this, but then divide by the coefficient for x over here. And then finally, plus a constant. And then you're done. Oh, wait, and over here, you just need to, at the last step over here, you can just combine this two. And then you can put that as 1 over 10. Oh, get right with this. Okay, wow, you guys did a lot today. Okay, take a deep breath. Okay, right, but you guys get a hang of it. That's really good. Okay, so this is what integrating rational function by partial fraction.
Because you think calculus is very boring and all that, but you make it fun for us. Yeah. Thank you.
I tried. Yeah, I really, really need to try because